Today we are happy to have Dr. Schmitz from CERN telling us about pulsar hints for gravitational waves from cosmic strings, question mark. So please.
That's important. Okay, yeah, so let's get started. Thanks very much for the introduction, and also thanks again for the invitation. I'm very happy to be with you today here and in this virtual seminar. It's also great to see several familiar names here on the list of participants. So hi to everybody. And I would also like to say that because, yeah, we are a small audience and I think, yeah, I have only prepared a certain amount of material. We should keep this very informal, so please feel free to interrupt me at any given time, ask questions, and we can also have part of the discussion already during the talk if you like. All right, so the title, as you just heard, of the talk is going to be Pulsar Hints for Gravitational Waves from Cosmic Strings. So we'll break this down into two parts. During the first part of the talk, I will give you a review, an overview of the recent developments in the field of pulsar searches for gravitational waves. Searches for gravitational waves based on pulsar timing arrays. And I will come to this in a bit more detail shortly and explain how this actually works. And then after giving you this recent update, I will turn to a specific interpretation of what these pulsar timing observations might currently be seeing. And then this is going to be gravitational waves from cosmic strings. The talk is going to be based on work and collaboration with several people. You see the list of names here. And during the second part of the talk, I will particularly focus on this most recent paper here and in this list, in which we discuss the emission of stochastic gravitational waves from a network of cosmic strings, in particular a network of metastable cosmic strings. I should also say that, yes, I give this talk as a fellow in the CERN theory group. I do not give it on behalf of the NANOGrav collaboration, but I should say that I'm also an associate member, at least an associate member of the NANOGrav collaboration. All right, so let's start with this picture here that I guess all of you have already seen many, many times during the last couple of years. So this shows the first direct detection of gravitational waves on Earth by the LIGO and Virgo interferometers back in 2015. So you can see the waveform of the gravitational wave signal that has been recorded by the interferometers in Hanford and Livingston here in the first row, or you can see the strength of the signal here in the frequency time plane, again for Hanford and Livingston. So this was certainly a breakthrough, a milestone in our quest for measuring and detecting gravitational waves. So what has been seen here in this first event was the merger of two black holes, a binary black hole merger with black hole masses of the order of 30 solar masses at a distance of around 400 megaparsec. And actually, well, the frequency, the gravitational wave frequency at which this event occurred is in the audio band. So this is something you can actually hear with your ears. So you can turn the signal into a real chirp audio signal, and let's try whether it works. So let me click this button here. I hope it's not going to be too loud for you. All right, that is the chirp signal that has been recorded by LIGO and Virgo back in September 2015. Let's do it one more time. Okay, so this is how the typical astrophysical signals sound like, the transient signals that our current generation of gravitational wave interferometers is capable of measuring, detecting. In view of this situation, the big question is, what's going to come next? What's going to be the next big milestone? And obviously, the next step will be to move from astrophysical sources, such as the mergers of binary black holes, binary neutron stars, or black holes merging with neutron stars, moving from those kind of sources to cosmological sources. And also, in comparison to the transient signals that LIGO and Virgo can currently measure, signals that arrive at the detector, spend some finite amount of time inside the detector, and then leave again. The next step is going to be to detect and, first of all, search for a stochastic background of gravitational waves that continuously reaches us from all directions and basically, permanently at all times. And such a stochastic gravitational wave background would then sound like something like this. So let me click here on this button again. Oh, I hope this was not too loud for you. Sorry if this was a bit too loud on your ears. This was more or less a white noise signal over a certain frequency bandwidth. And then this is how a stochastic gravitational wave background would sound like if it were located at the right frequencies and then converted into an audio signal. So after the chirp signal, this kind of noise signal is going to be the next major step in gravitational wave experiments. All right, so, and actually we've already gone the first step into that direction. Basically since September last year, there have been very exciting developments in this field. Namely, since September last year, there has been strong evidence for a new signal at nanohertz frequencies in pulsar timing array, PTA data. And during the next couple of minutes, I would like to discuss how PTAs perform their measurements and the kind of signal that they have seen since basically, September last year. All right, but first, to put us all on the same page, a few words about pulsar timing arrays, or PTAs. So the basic idea is to construct an array of pulses across the entire Milky Way, and then to use this array of pulses to basically construct a virtual gravitational wave detector that is almost as large as the entire galaxy, a galaxy-sized gravitational wave detector. Pulsars are highly magnetized, fast rotating neutron stars. You can see an artist's impression of a neutron star here in this image on the left-hand side. And then they represent extremely stable objects. So the rotation frequency remains extremely stable over an extended period of time, over long times. So pulsars provide us with this unique possibility to use them as ultra-precise clocks, ultra-precise stellar clocks scattered across the entire Milky Way, and basically set up this network of very precise timekeepers on galactic scales. So the rotation period typically of these pulses is of the order of a few milliseconds up to a few seconds. And especially the pulses with the shortest period or with the highest rotation frequency, so-called millisecond pulses, they often form in close binary systems. So this means that the neutron star has a companion in a binary system. It accretes material from the companion, and this accretion of material basically spins up the neutron star. It increases its rotation frequency and turns it into a millisecond pulsar. And then those millisecond pulses are the most stable systems and the ones you want to use for PTA measurements. All right. Another characteristic property of pulsars, and this is actually what gives them their names, is that they emit beamed radio pulses from radio jets from their magnetic poles. And in this magnetic axis here, the magnetic dipole axis is typically not aligned with the rotation axis. So that means that within one rotation, we only see this radio beam whenever it is aligned with our line of sight. Just like in the case of a lighthouse, where we also just see the light coming from the lighthouse if it points into our direction, into our line of sight. So this makes these pulses basically cosmic lighthouses that send a sequence of highly stable and regular pulses towards us in our radio telescopes on Earth. All right, and the basic idea behind these PTA observations and searches for gravitational waves is now to use this network of ultra-precise clocks, cosmic lighthouses scattered across the Milky Way, and look for tiny distortions in the pulse travel times that are caused by nanohertz gravitational waves in between us and the pulses across the Milky Way. And this is what you can see here in this image on the right-hand side. So we look at this area of pulses across the Milky Way. They send us this sequence of highly regular pulses. And in between, there might be a background of gravitational waves, as you can see here by this well, faint mesh, okay? And then these gravitational waves in between, they might distort space and time such that the pulse travel times are affected and can give us a clue about, yeah, the presence of gravitational waves. All right. How does this? Yes.
I'm sorry, can I ask a question?
Please.
So what's special about the millisecond pulsars? If I consider millisecond pulsars and nanohertz gravitational waves, there are huge difference in time scales. So what's special about millisecond pulsars?
Yes, what's special about millisecond pulsars is that they're extremely stable.
Okay, stability.
Yeah. So because they have the highest angular momentum and then basically are the best timekeepers. And for instance, I mean, even today, the most stable pulsars, they can really, in the millisecond pulsars, they can really compete with atomic clocks. And I think back in the day, maybe in the 80s, there were times when certain pulsars were better timekeepers than the most up-to-date atomic clocks. That's why you want to use millisecond pulsars, right? And you have to...
Is it really right? All millisecond pulsars are that stable? Because we want to compare the nanohertz. So the time scale is pretty long. So I wonder if all millisecond pulsars are that stable.
Well, I think there's a range of different, basically, quality properties among these different pulsars. So some pulsars may be more suitable for this analysis than others. That's also why, and then we'll come to this on the next slide, that's why it's so important to really understand each pulsar as best as well as possible. Yeah. So for each pulsar individually, you have to develop a noise model and really try to accumulate as much information about this pulsar as possible.
Okay.
And then if you perform these analyses, you can typically see how much the final signal is affected by including the data from one pulsar or not including the data from that one particular pulsar. So typically the signal is always dominated by a bunch of pulsars that perform best, and then others don't contribute that significantly to the signal.
Okay, thank you.
Right. But yeah, I mean, it's an amazing measurement technique because you have these very different timescales involved in the problem. So you have to monitor these pulses, which occur every few milliseconds, and you have to measure them extremely precisely, but you have to measure them very precisely over a time span of many, many years, right? Because we're looking for nanohertz gravitational waves. And nanohertz basically means one oscillation every few years, maybe just an oscillation every 10 years. And also because we know that gravitational waves propagate at the speed of light, or at least extremely close to the speed of light. That means that we're looking for gravitational waves that have a wavelength of up to several light years, or maybe even more than 10 light years. And to see these oscillations, these gravitational waves at these very low frequencies, you have to monitor and keep track of the pulsars for an extremely long period of time. And this is what the PTAs are doing. So they're trying to obtain as much data as possible over basically several decades. And then we'll see what the current status of these measurements are in a few minutes. All right. Yes. So let me show to you how this looks like in practice. So here is actually an example for some real PTA data, namely the most important observable that you're interested in. And then these are the residuals in the pulse times of arrival, TOA, the times of arrival. So for each individual pulsar, I, this is this little index I here, you can construct these timing residuals. Basically, you perform the measurement of the times of arrival, which enters here in the first term on the right-hand side. So you do the measurement on Earth, obviously, but then you want to convert this measurement into in a local inertial frame. So you relate this to the times of arrival an observer would see at the position of the solar system barycenter. Okay, that gives you the experimental value here on the right-hand side. And then you compare this to your model expectation, and this is what I just mentioned. For each individual pulsar, you have to come up with a very complicated timing model, and this is really where much of, almost most of the hard work goes into, because you have to model for each individual pulsar the rotation frequency, the time variation in the rotation frequency, first derivative, second derivative, the position, the proper motion, also the binary dynamics, if the pulsar is still a part of a binary system, and so on. So you try to do as best as you can here to construct this. The left with the difference is the timing residual, basically the variation in these TOAs that you cannot explain based on your timing model, and then a gravitational wave background would manifest itself in basically periodic variations in these timing residuals. All right. So in principle, I mean, it's hard to see by eye, but what you would like to see here and in these timing residuals in the plot on the upper left would be really some periodic variation at very low frequencies, some modulations which cannot be explained by the intrinsic pulsar properties, but something that basically operates residuals or the propagation time in between the pulses and our observatories on Earth. Okay, but so once you see these timing residuals, how do you know that you've really seen gravitational waves? And for this, you have to look at correlations among different pulses. And the main observable here basically is the angular correlation between pairs of pulses. This gives you the hallmark signature of a stochastic gravitational wave background signal. Gravitational waves are then expected to lead to quadrupole correlations. And then this is what you can see here in this plot on the top right. On the horizontal axis, we have the angle between any given two pulses in the sky. And on the vertical axis, the correlation of their respective timing residuals. And if in the timing residual, if the timing residuals really encode a gravitational wave signal, you would expect this particular shape here, which is described by this red line. This is the so-called Hellings and Downs curve, the so-called overlap reduction function for gravitational waves in these PTA experiments for the experts in the audience. And then you see that we expect a positive correlation if the two pulses that you consider are basically in the same direction in the sky. Then if they're separated by an angle of around 90 degrees, or let's say 270 degrees, then you expect a negative correlation. But then if the two pulses are back to back and separated by an angle of around 180 degrees, you expect again a positive correlation. And then this is sort of the holy grail of PTA searches for gravitational waves. Once you see that shape in the data, you can really claim strong evidence for the presence of gravitational waves in your data. All right, let's see how this compares to the most recent PTA data sets. So NANOGrav is one of these PTA collaborations, and it's the one in North America. And in September last year, they have presented strong evidence for a new stochastic process at low frequency. So they really see a new signal in the timing residuals for the set of pulses that they consider at low frequencies. They call this a red process because it's located at low frequencies. And in here, you can actually see this in the data. So this is the timing residual cross power spectrum, basically the power spectrum, the cross correlation power spectrum for the pulses in frequency space. The noise expectation, this is what you see here on the right-hand side. So this is more or less flat, but then you see an axis that goes above the noise expectation. And this is the new signal that they see. They can also fit this by a power law in terms of an amplitude and an index. And then here on the right-hand side, you see the 1 and 2 sigma posterior constraints on these two parameters of this very simple power law model. All right, so this is based on the most recent data set, 12.5 years, 47 millisecond pulses. As I said, this can be described by this power law. So formally, you can write down this cross power spectrum as this amplitude A, okay? Here in these units, this occurs or this enters as A squared, and then the power law index gamma, which is shown here on the horizontal axis. And of course, if you see that, it's not quite clear yet whether this is really gravitational waves. You have to wonder whether it's systematics, maybe some unaccounted for pulsar noise, solar system effects and clock errors. But at least the NANOGrav collaboration has performed lots of different checks, consistency checks, and then try to confidently rule out many of these possibilities here. So at the present stage, it's certainly a very viable possibility that this is not a systematic effect, but that this is real and something that is really part of the data. All right. And I think further support to this interpretation is also lent by the observations of other PTAs, because now in this year, there have been new announcements by other PTA collaborations that also basically see the same signal. So in summer, there was a paper on the archive by the Australians. This is the Parkes PTA in Australia. And then so they basically see the same signal here, the same plot of the timing residual cross power spectrum, again at high frequencies. I mean, high frequencies for PTA standards. You see the noise expectation, but then at lower frequencies, the signal goes up and then goes above the noise level. And again, they can fit this by a power law and then find these posterior constraints here. These contours down here correspond to the NANOGrav results. The PPTA results are shifted a bit further up to higher values of the amplitude and maybe slightly smaller values of the spectral index, but it's certainly consistent at the level of these uncertainties here. And the Parkes PTA collaboration also concludes that they find strong support for a common spectrum process if they analyze the data under the same assumptions as the NANOGrav collaboration. All right, so this was the status in summer this year, but it continues because now just very recently, last month in October, there has been a paper by the Europeans. So this is the European PTA, the EPTA or EPTA, and they put out an analysis searching for gravitational waves based on a rather small sample of pulses. So this is just based on 6 pulses that have though been observed for a pretty long time, I think more than 20 years, if I'm not mistaken. But anyway, so this is based on 6 pulses observed by EPTA, and then they can more or less confirm what has been seen by NANOGrav and Parkes. So again, at high frequencies, everything looks like noise, but then you see this excess here at lower frequencies. They can fit this again in terms of a power law and find consistent constraints, posterior constraints on the amplitude and the spectral index. All right, and I should also say that very soon there will be another analysis by the 4th player in this game, basically, which is the IPTA, the International Pulsar Timing Array Collaboration. This is not an independent collaboration, but this is just a joint collaboration of all the major 3 PTAs. So when EPTA, NANOGrav, and PPTA combine the data sets and analyze them together, this results in what is known as IPTA, the International Pulsar Timing Array. They will have their 2nd data release soon, and also a search for gravitational waves based on this. So stay tuned. And yeah, you can speculate what IPTA is going to announce based on what the individual PTAs have already seen. So yeah, things look very promising and certainly move into the right direction. Okay, so there is a signal. We can make the assumption that it's not any kind of systematics, and then I think this is well justified. But then the question is it really gravitational waves? And then for this, we have to look at these angular correlations that I mentioned and see whether we find evidence for this particular quadrupole pattern, the Helings and Downs curve. You can just look at the reconstruction of these angular correlations by NANOGrav and Parkes. This is what you get from the data. And again, here, this dashed blue curve is the Helings and Downs curve, and this black dashed curve here is the Helings and Downs curve. Right now, the evidence for this Helings and Downs pattern is not strong enough, but certainly it's also not inconsistent. So the fact of the idea that these error bars will shrink in the future and then basically asymptote towards the Helings and Downs curve is very realistic and can very likely happen in the near future with more data and more analyses. All right, you can at least say that, well, there's no evidence for a monopole correlation. This would just be a constant value up here, and the data really does not prefer just a straight line, which would be a fixed value independent of the angular separation. So there's no evidence for a monopole correlation. There's also no evidence for a dipole correlation. Dipole would just mean you go from +1 down to -1. This is not preferred by the data. And the evidence for the quadrupole is not yet conclusive, but it can very easily build up in the data as we put in more pulses and extend the data sets by longer observations.
Can I ask a question?
Of course.
Okay, so how many pulsars they use? I mean, the same pulsars are analyzed by NANOGrav and PARCS. I just wonder how,
Yes, that's a good question. So for NANOGrav, it's 47. And for PARCS, I think it's 26.
Yes.
Maybe 25 or 26.
And how many common pulsars, do you know?
Sorry, how many common pulsars?
Yeah, right.
Not too many. Not too many, just because of the location of the observatories, the telescopes. There's a number. Maybe it's order 10, but don't quote me on this. Maybe it's 10, maybe it's a bit less. NANOGrav has always used 2 telescopes, named the Green Banks Telescope in West Virginia and the Arecibo Telescope in Puerto Rico. And PARCS has used the PARCS Observatory down in Australia. So PARCS looks at the Southern Hemisphere and NANOGrav looks at the Northern Hemisphere, maybe also parts of the Southern Hemisphere. Yeah, there's some overlap, but not too much.
Yeah, I was asking this question because they may check the consistency, right? Seeing the same pulsars. Yeah.
Yes, absolutely. Yeah, I guess they can do this for pulsars that are part in both data sets.
Yeah.
But right now I'm not aware of any such pulsar-specific analysis. But I guess, yeah.
Should be consistent.
Yeah, should be consistent. I haven't heard anything about any inconsistency.
Right. Okay.
Right.
Thank you.
Yeah, and so as you're asking about the number of pulsars, EPTA in its latest data release or latest analysis just used 6 pulsars.
Yes.
And then this is a small number, so that gives you 15 pairs of pulsars. So 6 times 5 divided by 2. And then for EPTA, this plot does not look very impressive. Yeah, so basically they don't really have any error bars. They can just exclude something down here at the bottom and they can exclude something here at the top. That's why I'm not showing the EPTA plot. But again, also the EPTA data it's not inconsistent with a quadrupole. But yeah, this here is a bit more constraining. And the hope is that in the future, this will give us tighter bounds and hopefully converge towards the Henningsen-Downs curve.
Okay.
All right. So yeah, it's roughly half time for this talk. So I think it's a good time to slightly switch gears. So I've talked about the general principle behind PTA measurements and the signal that has now been seen by all the 3 major PTA collaborations. So very exciting. Everything is moving into the right direction. Let's now turn to the possible interpretation of this signal. So obviously, first I have to mention the basically standard astrophysical interpretation. And this is also what I think most PTA astronomers have in the back of their minds if they think about the possible origin of nanohertz gravitational waves. And then this would be the mergers of supermassive black hole binaries. So basically, the mergers of binary black hole systems that have formed after the mergers of entire galaxies. And then these mergers would constitute a background of gravitational waves just in the nanohertz regime, in analogy to signals from black hole mergers that we can probe at higher frequencies that come from systems that are slightly less massive, slightly smaller black hole masses. All right, so this is certainly a viable possibility, but it's also important to keep in mind that this comes with many open questions, many unknowns. The question is, where do these supermassive black holes at the centers of galaxies actually come from? What is their growth history? How do these binaries really form? At what rate do they form? At what rate do they actually merge? So suppose you have this galaxy merger. What is the time delay between the galaxy merger and the merger of the 2 central black holes? Is all of this still within the lifetime of the universe, or does it take significantly longer so that there's actually not enough time for these systems to merge? How do you get the 2 supermassive black holes close enough? In the end, you really have to get them down to a separation of less than a parsec to trigger this last stage of in-spiral and merger, which gives you the strong signal in gravitational waves. For this, you have to come up with some friction mechanisms so that you can basically dissipate of angular momentum and then get these two heavy guys really close together. So all of these are open questions. There are lots of ideas and models in the literature trying to address these questions. And if the signal should really turn out to originate from supermassive black hole binaries, then the exciting prospect here is that the experimental data will lead the field in the near future, and then we will maybe obtain answers to lots of these questions here, not by constructing more models, but just by taking more data and letting the data tell us what the properties and dynamics of these systems are. But it's also important to keep in mind that at present, excuse me, the present models, they struggle a bit to get the right amplitude of the signal. Yeah. So in these models and simulations, you try to estimate the local density of supermassive black hole binary systems. What turns out is that the current state-of-the-art models, they always tend to give you a slightly too low density, which results in a slightly too low signal. So in the end, that interpretation always gives you values of, let's say, here, the amplitude, which falls a bit short of what the PTA collaborations are now seeing. So from the PTA perspective, the signal that has been observed now is actually pretty strong. It's a strong signal, and it's difficult to really explain this in terms of just these astrophysical objects here. And then this has many people to speculate about at least a second component in the signal, or another primary component in the signal that really dominates the signal, that might be related to new physics, physics beyond the standard model. And here I'm giving just an incomplete list of interpretations that have been put forward. Cosmic strings, gravitational waves associated with primordial black holes, cosmological phase transitions, axions, and so on. And yes, because I have worked on that possibility and this interpretation, in the remainder of the talk, in the next 25 minutes, I want to focus on cosmic strings as a possible interpretation. All right, so just again, to put us on the same page, a brief reminder on what cosmic strings are and how they can give us a background of gravitational waves. Cosmic strings are a certain type of topological defects, one-dimensional topological defects that can form in the early universe after the spontaneous breaking of U1 symmetry. And once you've generated these cosmic strings, they form a network, which you can simulate here on the computer. And this network typically consists of long strings. You see these black threads here. These are the long strings, and they have an extent larger than a Hubble length, for instance. So they stretch across many, many Hubble lengths. They can in principle be infinitely long or just correspond to extremely large closed loops. And then you have also a population of much smaller closed loops, which looks like this these black specks of dust here in the simulation. And they are chopped off from the long strings when these long strings intercommute and intersect. And this network reaches what is called a scaling regime that is self-similar in time, and where the energy density, the fraction of energy contained in the network in relation to the total energy density of the background remains a constant fraction. Okay, you can parameterize the properties of this cosmic string network in terms of two important parameters. The most important one maybe is the cosmic string tension. So this is the energy per length, which has mass dimension 2. And typically this is quoted as G times mu, where G is Newton's constant. So G times mu is dimensionless. Another important parameter is alpha, the size of these small cosmic string loops at the size of production. And again, this is dimensionless because it measures the size of these small cosmic string loops in units of the Hubble length at the time of production. All right, so once you've got this network of cosmic strings, you can look at the production of gravitational waves or emission of gravitational waves from these cosmic strings. So there's basically, yeah, the main source of gravitational waves are the closed string loops, so these small objects here in the network. These cosmic string loops, they can then oscillate and emit gravitational waves basically at the fundamental frequency of the oscillation and the higher harmonics. This is one contribution, but then you also have localized features along these cosmic string loops that are referred to as cusps, and then kinks, where you have certain discontinuities on the cosmic string loops. And then they propagate at the speed of light and emit bursts of gravitational waves into certain directions. But then if you take all these contributions and sum them up, you obtain a stochastic background of gravitational waves. Okay, and because such cosmic strings can be formed in a variety of BSM models, basically all you need is the cosmological breaking of such a U1 symmetry. They correspond to a well-motivated and also viable interpretation of the NANOGrav signal and the signal that has also been seen with the other PTAs. So let me just show to you the outcome of an analysis that we performed last year, right after the NANOGrav data had come out. So this assumes basically the standard picture of Nambu-Goto strings, purely one-dimensional cosmic strings, basically the standard picture of cosmic strings, and the gravitational wave emission from such a network. So we scanned the parameter space in terms of the cosmic string tension, G times mu, and the loop size parameter alpha. And we can map the NANOGrav 1 and 2 sigma constraints onto our parameter space. And we find, very good agreement, or we can basically accommodate the NANOGrav data here across this large part of parameter space. So for instance, if you look at a cosmic string, a loop size parameter of 0.1, which is sort of a standard assumption, this is what you see in many numerical simulations, we can explain the NANOGrav signal for a cosmic string tension of around a G times mu of around 10 to the minus 11 or 10 to the minus 10. For instance, if you look at this circle benchmark point here, the corresponding spectrum looks like this green dot dashed curve. And by construction, it reaches the right amplitude here in the nanohertz range, but then it also continues up to higher frequencies and is potentially within the reach of these future experiments, such as LISA, Einstein telescope, and then Cosmic Explorer. All right. However, if you think that these cosmic strings are produced at the gut scale, then you would expect that maybe the underlying scale of symmetry breaking is of the order of 10 to the 15, now 10 to the 16 GeV. That gives you an estimate of the cosmic string tension of around 10 to the minus 7 or 8. This doesn't work down here. So if you want to accommodate such a large symmetry breaking scale, you really have to make alpha much smaller. So maybe if alpha is around 10 to the minus 4, I can reach very large values of the cosmic string tension. And then I can argue that the cosmic strings really have some origin in grand unification. Such a small value of alpha is still regarded to be a viable possibility. But at least in existing numerical simulations, there's some preference for larger values of alpha. So it's not quite clear whether this really gives you the most attractive possibility if you want to connect this to grand unification and very large values of the energy of the symmetry breaking scale. And another point is that this scenario, stable cosmic strings, all of them basically give you a signal that is a bit too small, a bit too faint at the high frequencies here in the audio band, so that this will not be within the reach of the current generation of gravitational wave interferometers. If you look at the prospects for Einstein telescope and Cosmic Explorer, everything is fine. So they would be able to see the signal here. But at least in this framework here, the current generation, LIGO, Virgo, and Kagra will not be able to see this cosmic string signal here at, let's say, frequencies of around 100 Hertz. The question is, can we somehow improve on the situation? And then is there a possibility to make maybe closer contact with physics really at the gut scale? And that this brings me to, basically the final part of the talk, where I want to talk about gravitational waves from a network of metastable cosmic strings. So the idea is to look at the embedding of cosmic string models into scenarios of
I'm very sorry.
Yeah, please.
No. Just one slide. I'm very sorry.
Yeah.
So if I look at the plot on the left, the lines almost coincide at frequency higher than 10 to the minus 8. What's the reason for that?
Well, I mean, this is basically by construction, because there's the parametric dependence on the two parameters alpha and g mu.
Right.
But basically we have chosen the benchmark points along this diagonal line here. So as you can put the circle, diamond, and the star on one diagonal, and along this diagonal, the effect of making alpha smaller and g times mu making g times mu larger, they compensate each other so that the signal looks very similar here at high frequencies. And we have to do this because by construction, we want to get the same signal strength here at nanohertz frequencies.
Right. Okay, I see.
Okay, so, I mean, you basically can look at a set of different curves if you just sample here this entire parameter space, and then you see the dependence on alpha and g times mu independently. But here, everything looks very similar because the curves are supposed to explain the same signal. They have to meet. They have to meet here in the nanohertz band to explain the NANOGrav signal.
Okay, I see.
All right. Yep. Okay, so I still have 15 minutes. I think this should be fine to say everything I wanted to say about metastable cosmic strings. So the idea is to embed your U1 cosmic string model into some grand unified scenario, maybe based on SO10. And that's very attractive also from a particle physics perspective, because it allows you to connect the idea of cosmic strings to other things like the generation of neutrino mass, leptogenesis. Maybe there's even some correlation with proton decay in this grand unified scenario. So here in this picture, I've taken this picture from this paper here by Hitoshi Murayama and collaborators from 2 years ago, where they basically quantify all the different possibilities how you can break down SO10 down to the standard model, or the standard model times some discrete Z2 symmetry. And depending on which symmetry breaking path you choose, there are many different possibilities to create cosmic strings along the way. So one famous possibility would be maybe to look at this breaking pattern here, where I have this intermediate gauge group G standard model, the standard model gauge group times U1B minus L. And then I break this down to either just the standard model gauge group, or I break it down to standard model gauge group times some Z2 meta parity. And in both cases, I get cosmic strings, which is indicated here by these blue arrows. And a possibility I want to focus on in the following now is this scenario here, where I break everything down to just the standard model gauge group without any additional stabilizing Z2 symmetry. And in this gut scenario, this actually results in what's called metastable cosmic strings, because the underlying theory based on SO10 does not know anything about cosmic strings. So SO10 does not give rise to the production of stable cosmic strings. SO10 just leads to the production of monopoles. So that means that the cosmic strings that you generate here at this intermediate symmetry breaking stage, they will be unstable against the quantum tunneling, against quantum tunneling events on these cosmic strings, where you produce SO10 monopoles and anti-monopoles. So this is what I'm showing here in this cartoon on the right-hand side. These cosmic strings, they can basically break down because you generate these SO10 monopoles along the cosmic strings. All right, an assumption here in this framework basically is that the population of monopoles, SO10 monopoles that you produce at very early times, maybe at the first symmetry breaking stage, that they have to be diluted away. Otherwise, if these SO10 monopoles are still around at the time of U1 symmetry breaking, will form what's called a string monopole gas, which is going to collapse very fast, and in which we do not expect to give rise to a significant signal in gravitational waves. So basically the idea is that first you have SO10 breaking, then inflation that wipes out monopoles as indicated here by this blue bar. And then after inflation, you basically start anew, you produce cosmic strings, which exist for some finite period of time, some finite lifetime. And then only after some finite time, you again nucleate these SO10 monopoles along the strings, which leads to the decay of the cosmic string network. All right, so in this recent work with Valerie Domcke and then Wilfried Buchmüller, we tried to describe the evolution of such a metastable cosmic string network a bit more precisely and also estimate the gravitational wave signal a bit more precisely. The starting point of this analysis is really to consider the decay rate of the network, basically the decay rate per string length. This has been estimated here or calculated a long time ago by people like Valerie and Presco in the 80s and 90s. And the number of decays per time per string unit length is then parameterized in terms of two parameters, the string tension mu and the mass m of these monopoles that you want to create along the cosmic strings. And then the ratio of these two mass scales, so basically m squared and mu, gives you a new effective parameter kappa, which appears here in the exponential and which can make this decay rate exponentially small or the lifetime exponentially large. So in this SO10 embedding, the strings are not really topologically stable, but they can decay on cosmological timescales. And if these two energy scales, mu and m, are not too far away from each other, so in some typical gut scenarios, you might speculate that this kappa or square root of kappa gives you a value of around order 1 or up to 10. Then this exponential here is not too small, and the decay can happen within the lifetime of the universe. This is what I want to refer to as metastable cosmic strings. On the other hand, if the two energy scales of SO10 breaking and U1 breaking are completely, vastly separated from each other, and the monopoles are much, much heavier than the energy stored in the cosmic string, then kappa will be very large, and this exponential will be very small, which means that you don't see any decay of the cosmic string network on cosmological timescales, and this is what I would refer to as quasi-stable strings. In that case, the gravitational wave signal will just look like in the stable case. All right. I also want to distinguish between two different types of monopoles, depending on the underlying UV completion. So you can distinguish between monopoles with and without unconfined magnetic flux. If the monopoles and anti-monopoles still feature some unconfined flux, then after monopole formation, you would expect that these monopoles emit massless gauge bosons, and then this rapidly leads to the annihilation of the monopole anti-monopole pairs. So in this case, these string segments would not really lead to any additional contribution in gravitational waves. However, if these monopoles do not feature any unconfined flux, then you produce these segments and they can still exist for some finite period of time, and they can only lose energy via the emission of gravitational waves. And then you will get a second contribution to gravitational waves from these cosmic string segments. All right. Yeah, I'm not doing particularly well on time. I still have 10 minutes. Let's see. So I think I still want to talk a bit about the physical scenarios that we consider, but I think I will skip some of the technicalities. And then if you're really interested in the full calculation, I invite you to look at the paper. So I rather want to show some, yeah, some nice pictures to you now and describe the physical scenarios that we have in mind, rather than just going through a long set of equations. I want to motivate another scenario where we can expect to obtain a network of metastable cosmic strings. So just one example is that you could think about hybrid inflation, which ends in a phase transition, a second order phase transition. This is typically called the waterfall phase transition. And it's a realistic possibility that the stage of hybrid inflation ends in a phase transition that is associated with a breaking of B minus L. So a very minimal model would look like something like this here in a supersymmetric language. T would contain the inflaton field. The fields S and S bar would be the so-called waterfall fields of hybrid inflation, and they would break B minus L via this expectation value here at the very end of inflation. And they can also talk to heavy neutrino fields and then induce heavy neutrino masses right at the end of inflation. And if this operator that gives rise to heavy Majorana neutrino masses looks like this with an s squared and an n squared, I can assign a B minus L charge of -1 to the field S. And in that case, I do not preserve any matter parity at low energies. So we really break down everything to the standard model gauge group. There's no remaining Z2 discrete symmetry. And this is the necessary criterion to form metastable cosmic strings. So that's a possibility here in this model. I just want to briefly mention that this is a scenario that we've studied in a series of papers over many years, as you can see here. That gives rise to a consistent cosmology that explains inflation, reheating, B minus L breaking, generation of neutrino masses, leptogenesis, and all of that. And we put all the constraints in this very complicated plot here, but in the end, there remains a viable region of parameter space that gives us a prediction for the energy scale of B minus L breaking, which is not too far away from what we would think where the gut scale is located. So this is a very promising scenario that gives us metastable strings, and the energy scales are just located at the right values close to the energy scale of grand unification. You can also basically cook up a model of metastable cosmic strings in a much simpler scenario. So here's a minimal alternative that has been proposed by Buchmüller, collaborated with Buchmüller earlier this year. So you can basically start with a theory based on SU2 times U1. You break it down to U1 cross U1 by SU2 triplets. That will give you an abundance of SU2 monopoles. Then you have to impose inflation to dilute away these monopoles. And then you break this gauge group down to a single U1 factor by SU2 doublets. And the breaking of one U1 gives you cosmic strings. But again, because everything is embedded into this UV theory, the cosmic strings that you generate in this U1 breaking stage here, they will be metastable against the nucleation of SU2 monopoles. So this is basically the minimal scenario where you can produce cosmic strings which are unstable against the nucleation of monopoles from some larger gut group at higher energies. All right, let's see. Yeah, so now it's the time is almost up. I want to talk about this slide, and then I will just directly jump to the results and show you some more plots. Okay, so just one word on our strategy, how to describe the dynamics of such a system. And for this, we divide the evolution into two stages, which we can identify based on the decay rate of the cosmic string network. So I introduced this parameter gamma d, which tells us at which rate we nucleate monopoles along the cosmic strings per unit time and per unit length. And during the scaling regime, we have this situation where we have an abundance of small cosmic string loops and long strings. You saw this image of the computer simulation. At some point, you will always have nucleation of monopoles at very large separations. They happen all the time, but initially they just happen on super horizon scales. But at some point then these segments begin to enter the Hubble horizon, and we can estimate this time. So gamma has mass dimension 2, and we multiply this by the length of the segments that we're interested in and the time scale that we try to estimate. So we want to know when do the Hubble length, when do the segments of Hubble size begin to enter the horizon. So the length we just put to the Hubble length here. H goes like 1/t basically during radiation domination, also during matter domination. So this gives us another factor of t here up in the numerator. So basically this condition is satisfied at times of around 1 over the square root of the decay rate. At this time, these super horizon string segments begin to enter the horizon. So we can distinguish between two different stages in the evolution. At very early times, we are still in the standard scaling regime. At this time, we have loops, which are chopped off by these long strings, and they emit gravitational waves. And then on these small, short length scales, they do not yet decay into segments. And we have the long strings, they decay into segments on super horizon scales, but this does not matter much for the emission of gravitational waves on subhorizon scales. This is basically the standard regime and gives us a signal very similar to the case of stable cosmic strings. However, then at late times, this is basically the decay regime, everything changes. This is where we then find the modification of the gravitational wave signal. So after this characteristic time scale, or when the scaling regime has ended, the loops on subhorizon scales, they continue to emit gravitational waves, but they can also break apart into shorter segments. And then these segments, they can also emit gravitational waves, but yeah, in a slightly different parametric way. But that gives you a contribution to the gravitational wave signal. If the monopoles do not have any additional unconfined flux, as I mentioned earlier. And you also have segments inside the Hubble horizon, segments that have either formed from these long strings at earlier times, or segments that originate from the breaking apart of these cosmic string loops. And then they give you additional contribution to gravitational waves. So what we do in the paper basically is to refine the analysis of gravitational wave emission by these new contributions here. Well, this is based on kinetic equations that allow us to track the number densities of these different objects. Yeah, so we have a kinetic equation for the number density of loops with a little circle here on top, and a kinetic equation for the number density of segments with a little tilde here on top. And this is really at the heart of the analysis, but because I'm running out of time, I want to just flash this at you and invite you to have a look at the paper to see how you set up this kinetic equation and how you solve it to really get these number densities which you want to calculate the gravitational wave signal. So yeah, just let me mention here the bottom line. This is a tough problem. So in the end, you have to solve partial, integral, differential equations in a large number of different cases. Yes, you have to look at these equations in the scaling regime, and then at the end of the evolution in the decay regime. You have to do this during radiation domination, during matter domination. You have to do this for loops. You have to do this for segments. And in the end, you can take all these different results, piece them together, and then estimate the gravitational wave signal. All right. So yeah, this is just one solution of such a kinetic equation. For the experts, it looks like in the case of stable cosmic strings, the modification now is some exponential decay factor here, which depends on our decay rate. So we see that after some finite time, there's an exponential decay or drop off in the number density of our loops in this case. So this is just one example. But then if you solve these kinetic equations, you can basically derive all the different number densities for loops and for segments during radiation domination, during the scaling regime, during the decay regime, and so on. So yeah, it's kind of a tedious case-by-case analysis where you have to solve this differential equation or integral differential equation over and over again for the different objects that you're interested in. However, once you've done that, you basically can plug them into your master equation for the gravitational wave power spectrum. So this is a standard expression. Yeah, maybe this is also familiar to some of the experts in the audience. Once you have the number densities of objects that emit gravitational waves, you can basically integrate over time and look and sum up the gravitational wave contributions from these objects at all different times. You include a redshift factor that accounts for the redshifting of energy in these gravitational waves. You properly normalize everything, and then you can generate plots like these here. So on the left-hand side, you see the final result of the entire analysis, which I didn't describe in much detail. But yeah, you see how the gravitational wave spectrum looks like now. The colorful curves here correspond to our case of metastable cosmic strings, and you can compare them to the dashed curves, which correspond to the case of stable cosmic strings. We can vary two parameters here. The color code gives you different values of g times mu. So this is the cosmic string tension. And then the different sets of curves, solid curves, dashed curves, they correspond to different values of this kappa parameter. So this is this separation of scales between the scale of SO10 breaking or the monopole mass and the cosmic string tension or the scale of U1 breaking. If this becomes larger, so if the two symmetry breaking scales are separated to a larger extent, then kappa becomes larger, and the suppression in the gravitational wave spectrum moves to lower frequencies. So if kappa or square root of kappa becomes very large, then everything will just move to the left here to lower frequencies, up to the point where it's no longer distinguishable from the spectrum from stable cosmic strings. All right. So we find that in this discussion of gravitational waves from loops and segments, the loop contribution is always dominant. This is an interesting technical result because there had been earlier work on the same topic where the conclusion had been the opposite, namely that the segments contribute the signal. We can characterize the power law behavior here, the rise in the spectrum at low frequencies. This gets like f squared. This is also an improvement over some earlier work that we had done here in this paper. So here we had just presented a very rough estimate. Now, based on this more careful analysis, we learned that this is an f squared behavior here, something that in principle you could also try to see in PTA data. And the bottom line, so I think this is basically the punchline that I wanted to arrive at, is that now in this case of metastable cosmic strings, we have the suppression here at low frequencies because the network is unstable. So we can slightly suppress the signal at low frequencies, and then to compensate for that and then still get the right amplitude for NANOGrav, we can increase the cosmic string tension. So now, in contrast to the stable cosmic string case, we can work with a larger cosmic string tension, which gives us a stronger signal here at higher frequencies, which means that this possibility or this scenario of metastable cosmic strings is now really within the sensitivity reach of these ground-based interferometers, the current generation, which was not possible for the case of stable cosmic strings. And yes, so we can also map this here into this parameter space. NT is the spectral index at nanohertz frequencies, and this is the amplitude. We can cover this part of parameter space, and then you see that this is consistent with NANOGrav and also PTA. Okay, so this is not the most recent version of the plot. This is an old PPTA bound, but the new PPTA data is also here in this part of parameter space, and it's absolutely consistent. Okay, let's see. Maybe just, so I think I can skip this slide here. This is how you can correlate the signal at low frequencies to high frequencies. And let me directly jump to the conclusions because time is up. So I talked about stable and metastable cosmic strings. Both of them are viable possibilities in the context of grand unification. If you talk about metastable cosmic strings, you have to combine this with some assumptions about inflation. Otherwise, you would basically reintroduce the monopole problem. So you want to have first the gut symmetry breaking that gives rise to monopoles, then inflation, and then you start again, produce cosmic strings, but which are unstable and can decay again into monopoles. And then as I try to argue that this gives rise to some exciting predictions for basically also the current set of PTA data. It's consistent with NANOGrav, PPTA, and EPTA, but there are also very exciting prospects for future experiments because it really gives you the signal that stretches across a large frequency range, all the way from nanohertz frequencies up to the audio band. In future work, would be interesting to explore a few other directions in parameter space. In our study on metastable cosmic strings, we kept the loop size parameter fixed at the standard value. Also play around a bit with the parameters that quantify the efficiency of gravitational wave emission. All we did so far was just an analytic attempt to describe the dynamics of such a network of metastable cosmic strings. So obviously in the future would be fantastic if this could be double checked or corroborated by numerical simulations. Would be fantastic if somebody could put this on the computer and numerically simulate a network of metastable cosmic strings. Another open question is, does this give rise to other interesting signatures? Maybe the annihilation of monopoles and anti-monopoles. Does this give rise to any additional signal and radiation? Maybe some CMB spectral distortions depending on the time when this happens. This is an open question, so I put a question mark here. And also from a broader perspective, it would be interesting to look at gravitational waves from different types of maybe more realistic cosmic string scenarios. For instance, gravitational waves from superconducting strings, wiggly strings that have more substructure on smaller scales, and so on. But this is left for future work. So for now, my time is up. And so let me thank you for your attention. Thank you very much.
Okay, thank you very much for the interesting talk. Other questions or comments?
Yeah, and sorry for going over time. We had some discussion in between already, but yeah, I was not particularly good staying in time.
May I have a simple question about
of course.
String dynamics? If I just consider the web of strings, then I think the dynamics can be pretty complicated, even classically. In that case, probably you need to do very complicated dynamical calculations about the movement of strings to really generate the gravitational wave and so on. Is it right? Or you have a better way to do?
Yes, I think in principle, the dynamics are very complicated. But what is very interesting and actually kind of amazing is that you can capture lots of the complicated dynamics just in a handful of effective quantities, effective parameters.
Yeah, right, yeah.
Typically, if you look at the standard case of stable cosmic strings, to run these numerical simulations can be very non-trivial and uncomplicated, but still it turns out that you can describe everything analytically to a very good precision in an analytical model. It's called the velocity-dependent one-scale model. It's a complicated name. It's typically abbreviated as the VOS model. And the idea is that there's only one characteristic length scale involved in the problem, which basically determines the correlation length in the network, the typical distance between long strings, which also determines to some extent the size at which the cosmic string loops are formed. And it turns out that this analytical description, the VOS model, performs very well in comparison to numerical simulations. To some extent, it's necessary to take some phenomenological parameters in this analytical description and basically normalize them or gauge them based on numerical input. Yeah? So you have a simple analytical description. You have some parameters where you think, okay, they have to be there, but you don't know the value. Then you run the numerical simulation and you get some idea which value, which number I should use for these effective parameters. And then this is also the same for the emission of gravitational waves. This is what I call the capital gamma or gamma tilde here. This is an effective parameter that quantifies the amount of gravitational wave power emitted by cosmic string loops. And so the actual process, the microdynamics, is very complicated. So you really have to do a hard calculation or some numerical simulation to see how gravitational waves are emitted. But then in your effective description, there's just one parameter that captures what is the efficiency, what is the power of gravitational waves emitted. You normalize this, you gauge this by using the numerical input. Then you put a number. So in this case here, it's just one number, a 50 in certain units. And then you can use this in your analytical description. This is, I would say, the state of the art. And then this is what we're trying to do here in this analysis. Yeah, so we try to work analytically as much as possible. And then where necessary, we fix certain effective parameters based on these numerical simulations. And then we think that this is a good first order approximation. But then in the end, to validate this approach, it has to be cross-checked against explicit numerical simulations.
Right, yeah. I guess this kind of effective description makes sense in the sense that the space-time is still homogeneous and isotropic to some extent, right?
Yes, absolutely. I mean, the network has certain symmetry properties, and it reaches this scaling regime. It's a self-similar evolution.
Right.
And then that makes the description much simpler. So as far as I understand, everything that happens at earlier times, you have the production, the generation of the cosmic string network, and it takes some time until this scaling regime has been reached. Yeah, so the system has to find this attractor solution, and this approach to the scaling attractor solution is much more complicated, and really requires some numerical simulations. But as soon as you have found this attractor solution, which exhibits these simple scaling laws and scaling behaviors, the effective description becomes much simpler.
Yeah, sure. Thanks.
Further questions or comments?
Hello.
Hi.
Hi. Thank you very much for the nice talk. In the middle of your talk, you mentioned there are a number of interpretation of the signal into the new physics.
Yes.
And there are several options. And can you distinguish different new physics scenarios at what level?
Yes, I mean, at the moment, it's very hard because the error bars, in a sense, are still very large. I think in the end, the best that these PTA experiments can do in the near future is to narrow down the viable parameter space here as much as possible. So you really want to measure the amplitude and the spectral index, the spectral tilt, as precisely as possible. And then, for instance, one interesting reference solution or benchmark solution would be these supermassive black hole binaries. They give you a very distinct prediction for the spectral index. Let's see. Yep, you can see this here in this plot. So this is the gravitational wave spectrum as a function of frequency. And then these triangles and then well, all of this here, this corresponds to the background from gravitation, supermassive black hole binaries. This spectral index is theoretically predicted, and it corresponds to, let's see, it corresponds to always this black dashed line here in these plots. So in these units for gamma, this is one value, 13/3, and then the more the measurements eventually deviate from this number here, the more likely it becomes that it's maybe something else, or that it's the sum of different contributions. I mean, it's interesting if you look at this here. So the blue ellipses are Parkes PTA. This down here is NANOGrav. Now they really overlap here in this region, which is very close to the supermassive black hole prediction. But who knows? I mean, at the moment, the error bars are still very large. Yes. And another point is that, I mentioned this, the current models of supermassive black hole binaries, they don't really give you the right density of such systems at low redshift. So it's a bit hard to really get the large values of the amplitude up here. But in any case, so in the near future, within the next 10 years or so, I would say measuring these observables here will be our best opportunity to distinguish between different models. Maybe one last comment to answer your question. I had a slide here which I skipped. NANOGrav also did some projection into the future. So let's see, where is it? It's here. Yeah, so this was a paper in last October. They emulate data sets into the future. They look at 16, 18, 20 years of data, and then try to estimate what they will be able to do with such larger data sets. And they say that starting with more than 20 years of data, they will be able to detect deviations from a simple power law, right? So what I showed to you was basically a 2-parameter fit amplitude and spectral index. And let's say in some kind of CMB language, you could say that starting from 20 years of data, you can also look at the running of the spectral index, and then further in the future, you might also be able to look at the running of the spectral index. So basically, you will become sensitive to the first derivative in this log-log plot, second derivative in the log-log plot, and so on. Yeah. It really boils down to the reconstruction of the signal shape. Yeah. So the better we know the signal shape, whether it's just a flat power law, whether it's curved, second derivative, third derivative, and so on, the better we will be able to distinguish between different interpretations.
Thank you.
Are there further questions or comments? Okay, otherwise we might thank Kai again. Thank you.
Yeah, thank you very much. Thanks for the nice discussion. Really appreciate it. Okay.
See you
Hope
next
to see you
time.
soon. Yeah. Thank you. Bye-bye.
Bye-bye.